Okay, we are live on YouTube.
Okay.
So I'll pause. Okay, greetings, everyone. You have joined the event being hosted by the Silicon Valley chapter of the IEEE Computer Society. I'm Vishnu Pendyala, the chapter chair. As the largest chapter in the Silicon Valley section of IEEE, we are proud of our over 3,500 subscribers on our mailing list. We have a robust Twitter following of more than 12,300. We hold a unique position to our strategic location and the wealth of expertise available to us. And today's talk is on artificial intelligence driven smart digital diagnostics and therapeutics for neurological disorders. Uh, so, we all know neurological disorders are a leading cause of disability and death worldwide. Early detection and efficient management of these disorders can provide significant health benefits. By providing real time data driven insights, AI driven methods meet an urgent need for early detection and management of these disorders. So, in this talk, Professor Phoha will present the potential of AI driven early diagnosis and digital therapeutics, abbreviated as DTX, for neurological disorders. Using the unique properties of data generated through neurological anomalies and disorders, one can use AI methods such as transfer learning from existing knowledge, one shot and few shot learning from spiking and sparse data, and hidden Markov models to find underlying relationships and causes of malignant neurological disorders. The speaker will show how the generated data can be captured through smart wearables and phones, how uncovering relationships provides insights for digital rehabilitation, and how using augmented reality and virtual reality provides tremendous potential for cognitive therapy, psychiatric assessments, and rehabilitation. Professor Poha will outline a proof of concept smart diagnostics enabled mirror and discuss security issues in smart diagnostics. So, a little bit of introduction to Professor Poha. Professor Vir V. Phoha is currently a tenured full professor of electrical engineering and computer science in the College of Engineering and Computer Science at Syracuse University, New York. His research interests includes machine learning, nonlinear prediction, hidden pattern detection and correlation, and knowledge discovery and analysis. Professor Poha has supervised 20 PhD students and 65 master students. He is a fellow of AAAS, AAIA, IEEE, NAI, and SDPS. He is an ACM Distinguished Scientist. He has won many research awards, including the 2017 IEEE Region 1 Technical Innovation Award for contributions to behavioral biometrics. So before I turn it over to Professor Poha, just wanted to let you know that you can feel free to post your questions on the chat window. Professor Poha would answer them towards the end of the presentation. And the links to the video and if the slides are provided, the slides will be posted on our website in about a week because that's a frequently asked question. And yeah, without much ado, I um, give it away to Professor Poha. Professor Poha, please take it away.
Okay. Thank you. Thank you, Vishnu. Thank you for a very nice introduction. And it is my privilege and honor to talk to IEEE audience and uh, it is great to share my thoughts with all of you. So what I will do is I'll go ahead and start the presentation. And the way I have organized the presentation is that very briefly, I will describe what is multiple sclerosis and what is stroke. And I will give a very brief introduction of AI and the AI-driven methods and how they may be used in the diagnostics and management of MS and stroke. Uh, to do that, I think it was, I thought it may be a good idea to give some foundational basics of AI and then talk a little bit about generative AI, recurrent neural networks, transfer learning, and diffusion models. I chose these models because we have, in our work, we have seen many applications of these models in real world problems. Finally, I will give a very generic introduction to AR VR and talk a little bit about a proof of concept system that we are working on. So, the neurological disorders are a leading cause of disability and death worldwide. It is very important to do an early detection and efficient management because that can save or even mitigate the effect of these disorders. For example, the prevalence is so much that in 2021, it was reported that almost 43% of the global population, which is approximately 3.4 billion, is affected by neurological disorders in one form or the other. Now, all of them are not MS and stroke, but some form of neurological disorders, the population, about 43% of the population is affected. And there is a 39% rise in neurological disease-related deaths over the past 3 decades. So managing neurological conditions such as stroke and multiple sclerosis, or I will call it MS, is very crucial because if there is an early detection, then it is vital to regaining lost motor skills and cognitive functions. And 60% of the stroke survivors develop long-term disability. So it is very, very crucial to detect it at an early stage, uh, preferably even before the onset, to see what the symptoms indicate. So just a little bit more statistics. Every 40 seconds, someone in the United States has a stroke. Every 3 minutes and 11 seconds, someone dies of a stroke in the United States. Stroke is the fifth leading cause of death in the United States, and about 795,000 people in the United States have a stroke each year. Stroke-related costs in the United States were nearly 56.2 billion between 2019 and 2020. So there are almost similar statistics for MS, but I just put one. That is, it affects over 1.8 million people worldwide. It is more common in young adults and females. Uh, Sorry, I think yeah. So what is a stroke? A stroke, also known as a brain attack, occurs when blood flow to a part of the brain is interrupted or reduced, preventing the brain tissue from getting oxygen and nutrients. And you can see here that, so for example, in these arteries and veins, if some part is obstructed, that will lead to a stroke. There are basically two types of strokes. Ischemic stroke is caused by a blockage in the artery, and it accounts for about 85% of the strokes. And hemorrhagic stroke is caused by a blood vessel bursting in the brain, and that spreads the liquid, and that is what is hemorrhagic stroke is. And ischemic stroke, where the blockage of the arteries comes, is about 85% of the strokes cases. So in multiple sclerosis, which is also called an autoimmune, it is a chronic autoimmune disease affecting the central nervous system. And in this case, the immune system attacks the myelin sheath covering the nerve fibers. So if this is the nerve fibers, this, for example, here, and I draw over it, this sheath is eaten away. And the symptoms and causes of the MS are visual changes, numbness, tingling, muscle weakness, coordination issues, fatigue, and cognitive changes. There is no known exact cause, but it involves immune system malfunction. There are genetic factors and environmental triggers. The risk factors, mostly for ages 20 to 40 years, are more common in women, uh, uh, especially if they have a family history of MS. It's caused by low vitamin D levels and also by smoking. The diagnosis and treatment requires MRI, spinal tap, blood tests, and nerve conduction studies. There is no cure, but treatments include corticosteroids, disease modifying therapies, physical therapy, and lifestyle changes. So, how does AI play a role? Very first is the early diagnostics of neurological disorders. Once we know, uh, uh, in addition to early diagnosis, it may be very helpful to see causal and interrelationship between the various uh, functions of the body, various environment, genetics, lifestyle, as well as comorbidities. The third role is the management of the disease or digital therapeutics, where AI can play a tremendous role because of the AR, VR, and because of the advances in artificial intelligence. It provides real time data driven management of neurological disorders. It's very prevalent now because of the wearable devices and real time feeding of the data from human body. So typically, uh, it AI is going to play a transformative role. Very first is personalization. That means now we can tune the therapeutics to an individual's need, individual's body type, and the medication, how that person affects, uh, reacts to that in medication, and the exercise programs based on the stamina, the age, the body type, and various other factors. The predictive analytics is another place where AI can play a significant role because it can predict the future health states based on the current and historical data, and it can help in early intervention and prevention. Enhanced engagement, because you can now provide interactive and adaptive content, virtual coaching, gamified health activities, and real time feedback. Automation and efficiency, it can AI can now automate routine tasks, for example, patient monitoring, data analysis, and thus freeing up the healthcare professionals to focus on more complex cases. And finally, and perhaps very important, is the data-driven insights, uh, which can, because AI can analyze large data sets, large similar data sets, and uncover insights that may be missed by human analysis. And one can use these insights to inform treatment plans, identify at-risk populations, and improve overall health strategies. So, what is AI? So, AI is the science and technology to simulate human intelligence by machines and computers. So, for example, autonomous vehicles, crop analysis, drug discovery, medical diagnosis, generative AI tools. The idea is that if we can simulate human intelligence by machines and computers, then that is what we are referring to AI. A subpart of AI is machine learning, and it involves deep learning and rule based, which is based on human decision making processes that can learn and generalize. So, AI one can classify into two broader segments, what is called a narrow AI or artificial narrow intelligence, and it is referred to in literature as ANI, which is trained and focused on specific tasks. The examples are Apple's Siri, Amazon's Alexa, IBM's Watson X, and self-driving vehicles because they are focused on a specific task. As opposed to narrow AI or ANI, there is what is called a strong AI. And strong AI, again, has two components. One is artificial general intelligence and or artificial superintelligence. AGI as well as ASI, they aim for intelligence which is equivalent to humans, and it's self-aware consciousness, uh, uh, ability to solve problems and can plan for future. And that is what would refer to artificial general intelligence. But when we go to artificial superintelligence, it surpasses the human abilities and intelligence, and at present is mostly theoretical. So examples are of artificial superintelligence would be superhuman, and very first inclination of ASI was a rogue computer assistant in 2001 in the movie A Space Odyssey. So I've given a small diagram to show overall relationship. You will see ASI is the superset. Then you have rule-based systems, then narrow AI and strong AI. And within strong AI, you have superintelligence and machine learning, which covers both of these. So, a very active area now is generative AI. So, generative AI is what is mostly refers to deep learning that takes raw data, for example, Wikipedia, works of Rembrandt, etc., and can generate statistically probable outputs. Uh, it encodes a simplified description of training data and generate new work that may be similar but not identical to the original data. So a very good example that I usually give is that if a neural network or deep learning network has learned to move the thumb, to bend the thumb, and and it has also learned to wiggle the finger. So these are what are the specific tasks that the deep learning has learned. But if we can combine these to able to pinch or bend the thumb by combining this thumb and this finger, then that is an example of generative AI, which is taking two basic components and creating a new action which it was not trained on. So it is generating a new concept, it is generating a new action, but basic learning is only on moving of thumb or bending of thumb and moving or wiggling of finger. So how does deep learning work? So deep learning is multiple layers of interconnected nodes. And you will see here the input node, hidden nodes, and output nodes. And they need not be only one node, they can be multiple nodes. And the idea is that you have a training exemplar and an output, which is the desired output, and the error is propagated back to adjust the weights between the neurons. It is typically massive set of neurons in billions. For example, in large language models, you will have billions of neurons. And for small activities, you may have smaller neurons, but LLMs, etc., have very huge, massive set of neurons. Uh, because of extensive computations, it requires massive resources and typically high performance GPUs and calculations in multiple cores with large memory. Distributed computing is good, and most of the applications that I'm familiar with are typically in JAX, PyTorch, TensorFlow. So a little history of uh, AI. It kind of started in 1950 by Alan Turing in his book Computing Machinery and Intelligence, and he posed a question: can machines think? He proposed a Turing test, and what Turing test is basically if you have a curtain and you put a machine on the back or a computer on the back and a human on the back, and somebody queries that question or asks a question, then the person who is asking should not be able to differentiate whether the answer is by a computer or a machine or by a human. So that means the computer has human-like, or there is no difference between what a computer responds and what a machine responds. So if the computer can pass this test, that means it can fool the human interpreter, then it has passed the Turing test. In 1956, John McCarthy from MIT introduced the term artificial intelligence, and then Newell Shah Simon created the first running AI software program called Logic Theories. 1967, Mark Rosenblatt, Mark won the perceptron, a neural network that learns. Then Minsky and Pappert's book, Perceptrons, argued against this neural network. And I will give a small example in the subsequent slides. What was the core of their argument? Basically, this argument kind of stopped the progress of neural networks for almost 10, 20 years, almost 15 years. But in 1980, I would say 10, 15 years, because 1967 and then 1980s, mid 1980s, the backpropagation neural network became very popular. And I will show you why this happened. 1997, IBM's Deep Blue beats the world chess champion Garry Kasparov. That was a milestone. 2004, John McCarthy wrote a paper, What is Artificial Intelligence, and formally defines AI. Basically, I've taken some concepts from John McCarthy's paper in defining AI in the first few slides, where you want to mimic human intelligence. 2011, IBM Watson beats champions Ken Jennings and Brad Rutter at Jeopardy. This was a milestone. 2015, Baidu's MinWab supercomputer uses convolutional neural networks to identify and categorize images better than an average human. Again, that was a milestone which Baidu's MinWab supercomputer could use using CNNs. 2016, DeepMind's AlphaGo program using deep neural networks beats Lee Sedol, the world Go player. And you can see the possible moves are about 14.5 trillion after just 4 moves in in the in the AlphaGo in the game Go. So in 2023, there is, and now as well, there's a large rise in large language models such as ChatGPT, Microsoft's Copilot, and so on. So this has expanded so much that you can see high school students using ChatGPT in their assignments to write essays, to basically handle many, many things in their daily lives. Some of it is misuse, some of it is good use, but it is kind of revolutionized. It has had a great impact on the overall activities, at least in more technical areas. So, the underlying what is the underlying concept between deep networks? The core is a neuron which has an input, which we can call x1 through x1. Each is connected through a weight, and the output is y, which is run through a nonlinearity. So you multiply weights by the inputs and run it through a nonlinearity. The simple nonlinearity can be a threshold theta. If this value is less than theta, then you put a value 0, otherwise you give it a value 1. But you can also have sigmoidal, graded response. But so there are various nonlinearities. And a simplest implementation will be that if you have two input, for example, 0, 0, 0, 1, 1, 0, 1, 1, then you can implement an AND gate and also an XOR gate. So 0, 0 gives you 0 because both have to be same. This is 0 because they are not both same. They are both different, 0, but 1, 1, they are same, so you have 1. And in XOR, you get 0. They both have to be different, then 1, 1, and 0. So what Minsky, so you can implement this gate by using the weights W.5, 0.5, and theta is equal to 0.6. And you can see these equations Y come out to be, this is 0, And if you put 0.6, then this is less than 0. So this is 0. This is less than 0. This is 0. And this is 1. So these values uh, implement AND gate. And pictorially, you can see that if you plot 0, 1, 1, 1, 1, 0, 0, 0, you can kind of draw a straight line and this will separate these two. So you can use a perceptron to classify or build an AND gate. But what happens is that if you have an OR gate, there is no way you can draw a straight line to separate these two classes, because 1, 1 and 0, 0 are in one class, and 0, 1 and 1, 0 are in separate class. And that is what Minsky and Papert said, that neural networks cannot solve a simple XOR problem. However, what you will see that if we take more layers, and for example, if we take 1, 2, or 3 layers, then it can create very complex boundaries. So you don't have to have just one layered neuron. You can have 2 or 3 layers and it will solve many complex problems. As a matter of fact, there is a theorem which shows that any 3 layered neural networks can solve almost any, can create boundaries, that means the separation boundaries for very high degree polynomials. So in a practical sense, they can solve almost any problem. But if you have billions of neurons with multiple layers, you can make it to learn speech, you can make it to learn text, you can make it to learn anything, and you can generate various components from the same. And for example, if you have explainable AI, you can say which part of the neurons are learning which part, and which parts of the neuron are learning which part of the input, and then you can manipulate to create different combinations of activation of these neurons. So for example, if you're learning an image and you know that the legs are being learned by this, a human image, and you have another image and the face is being learned by here, say of a lion, then you can combine human legs with a lion face to produce an image which is a lion with a human legs. So various combinations uh, you can mimic, and actually you can do it a query driven system, but the underlying concept is the same, that you have various neurons and you can make various neurons active, and it can be query driven. And this is possible also because of the explainability of the work in explainability of neural networks. And so the idea is that these are mimicking the human brain, and that's why I kind of superimposed the basic model of the neural network with the human brain. So, what are various forms of neural networks? I thought it will be good to give a very quick description of major components. Typically, CNNs, convolutional neural networks, recurrent neural networks, autoencoders, and uh, generative adversarial networks. So, convolutional neural networks are used primarily in image processing and vision, and at least three main types of layers are involved: a convolutional layer, a pooling layer, and a fully connected layer. The convolutional layer works and reworks the original input. Detailed patterns can be discovered by convolutional layer. So earlier layers of CN detect simple features like color and edges of an image, and as the data moves through the layers, the network recognizes larger shapes and eventually identifies the object. I thought it'll be good to give a very quick, simple example. So if you have an input which is 213, say 3 by 3 matrix, and you have a kernel which is 1001, and you can run the kernel by multiplying kernel 1001 on 2110, and you will see multiply 2 by 1, multiply 1 by 0, multiply 1 by 0, and multiply 0 by 0, and you will get the 2. So the output will become 2, 3, 2, 1, and you can run this kernel over the whole matrix, and you will get the output 2, 3. So how do we use CNNs in stroke and MS? The typical applications are that you can do lesion detection and segmentation used to analyze MRI and CT scans. to detect segment stroke lesions, which is very crucial for planning the treatment. You can use it to predict outcomes, can predict the outcomes of stroke treatments by analyzing imaging data and clinical parameters. It's helpful in potential recovery and planning personalized rehabilitation programs. Automatic diagnosis assist in the rapid and accurate diagnosis of stroke by differentiating between ischemic and hemorrhagic stroke. So that becomes very essential for the timely and appropriate treatment, because the treatment for ischemic stroke is very different than the treatment for hemorrhagic stroke. So if you know beforehand what type of stroke a person is dealing with, then it becomes very crucial in the diagnosis and recovery. Treatment planning by analyzing the image data, CNS can help in planning interventions such as thrombolysis or thrombectomy, which is kind of taking the parts off and ensuring that patients receive the most effective treatment based on their specific conditions. In MS, again, almost similar things: lesion detection and classifications in the MRI scans, and they can differentiate between active and inactive lesions, which is important to monitoring disease progression and treatment response. Disease progression prediction, which is very crucial in MS, because autoimmune system, as it starts to eat away, the conditions of the patients can become worse. So you can analyze longitudinal MRI data to predict the progression of MS, and it helps in identifying patients at risk of rapid progression and adjusting the treatment plans. Patient stratification, it can classify, one can use CNNs to classify patients into different categories based on disease severity and progression. So you can then help tailor the treatment strategies to individual patient needs. Monitoring treatment efficacy by comparing MRI scans over time, CNNs can evaluate the efficacy of disease modifying therapies. It can help in optimizing treatment plans and improving patient outcomes. So, what are recurrent neural networks? They are typically used in natural language and speech recognition and applications because they use sequential or time series data. They do take a memory as an intermediate component and take the information from prior inputs and feed it back to the input to a neural network. They use backpropagation through time, and BPTT, or backpropagation through time, differs from the traditional approach in that BPTT sums errors at each time step. So how RNNs are used in stroke and MS? Again, predicting the stroke onset is because you have an analysis of time series data, and especially for wearable devices like smartwatch, smartphone, smart ring. So you have a time series data which is continuously coming, and you can analyze these to predict stroke. It can, for example, monitoring vital signs and other health metrics. It can identify the patterns that precede a stroke. Sometimes there is the patient cannot speak, there is a pain, patient cannot breathe. So these are the onsets, but much before that, there are predictors of stroke onset, and it can be, and if you have wearable devices, they can predict using RNNs. In rehabilitation and recovery, especially from physical therapy sessions, RNNs can adapt the exercises to the patient's progress, ensuring that the rehabilitation process is effective and tailored to individuals' need. Speech and language therapy, if the stroke patients often suffer from aphasia, which is a condition where they cannot communicate. And RNNs can assist in speech and language therapy by analyzing speech patterns and providing real-time feedback. Monitoring and predicting outcomes, RNNs can track a patient's recovery progress and predict long-term outcomes based on their rehabilitation data. This helps healthcare providers adjust the treatment plans as needed to optimize recovery. MS, almost the similar things, but you have a long, here the RNNs can analyze longitudinal patient data, including MRI scans and clinical records to predict the progression of MS. It can assess the severity by integrating multimodal data, just as neuroimaging, electronic health records, and clinical notes. Uh, RNNs can also do monitoring treatment response by track patient responses to various treatments over time, providing insights into the effectiveness of different therapies and the early detection of relapses. Uh, by monitoring ongoing patient data, RNNs can detect early signs of MS relapses. It will allow timely intervention, potentially reducing the severity and impact of the relapses. One of the very active areas in artificial intelligence is what is called generative adversarial networks, or GANs. These are a class of machine learning frameworks designed by Ian Goodfellow and his colleagues in 2014. Typically, it involves two neural networks, a generator and a discriminator, which are trained simultaneously through the process of competition. The generator creates the synthetic data, for example, images, text that mimics the real data, and it starts with random noise and learns to produce data that becomes increasingly realistic over time. The discriminator then evaluates the work of the generator and distinguishes between real data and the fake data, and it provides feedback to the generator to improve. So basically, they are two working in conjunction. One is generating, the other is separating and seeing how good a job the generator is doing. And if there is an error, it feeds to the generator to improve the work. In adversarial training, the generator and discriminator are trained together in a zero sum game. The generator aims to produce the data that can fool the discriminator, while the discriminator aims to correctly identify real versus fake data. This adversarial process continues until the generator produces data that is indistinguishable from the real data. So GANs are a subcomponent of generative AI, and is typically used in, for example, you have to create an attack on a system or so on, or you have to fool the system. Then GANs are very effective there in that. The key components are loss function, where both networks use loss functions to measure the performance, and the generator's loss function measures how well it fools the discriminator, while the discriminator's loss function measures how well it distinguishes real from fake data. The training involves alternating between updating the generator and the discriminator. This iterative process helps both networks improve over time. So I want to go very quickly on GANs in stroke and MS. In stroke, again, data augmentation for rehabilitation, because GANs can produce the data which mimics the real data. So if you don't have much data sets, then GANs can be very helpful to generate synthetic data. So it can generate synthetic kinematic data, whether it is movement data, and closely mimics the movements of patterns of stroke survivors. So you can use this data to train machine learning models, improving the accuracy of activity recognition systems used in stroke rehabilitation. Note that you can actually specifically tailor to an individual for GANs to generate a data which is particular to that individual who has had a stroke. So, lesion segmentation, GANs are used to enhance the segmentation of stroke lesions in medical imaging. By generating realistic synthetic images, GANs can help improve the training of segmentation models, leading to more accurate identification of stroke affected areas. And then simulating post stroke movements. GANs simulate realistic post stroke reaching movements, capturing the complex temporal dynamics and common movement patterns, because this can help. You cannot predict how a patient will react, but you can use generate GANs to produce different types of movement, so you can then adjust the treatment plan as well as the uh, exercises to simulate those parts of the body which have been affected by stroke. Almost similar things you can do for MS and lesion specific image synthesis. where it can synthesize high contrast MRI images from low contrast inputs by generating uh, synthetic data to enhance the visibility of MS lesions, and it can add more data for diagnostic models, and it can predict disease prediction by generating synthetic data of predicting how the disease will progress and generating synthetic data related to the progression of the disease. So the third model I talked about, want to bring very briefly, is what is called a diffusion model, and it's been very active. It is mostly used in image generation, and model starts with a clean image and gradually adds noise to it over a series of time steps. So, for example, you see an image of a dog here, you add noise, you keep on adding, and eventually you reach to a point where the image of the dog is not visible at all, is not recognizable at all. So, this is a forward diffusion process. The reverse diffusion process is that the goal of the reverse diffusion process is to learn the reverse process, but that given a noisy image at any time step, the model learns to predict the slightly less noisy image. So you're going back and adding uh, noise to it or removing noise to it to go towards the original image. So it is used in, so for example, here you will see inputs in diffusion model, and these are pure noise images, and then you get back and you get a different image of the dog from adding different types of noises to it. So during image, it's very commonly used to generate images which are similar to the original image but have different uh, visual appearance. So I took the image of a dog and a different dog and a different dog to generate from one image several different images. So how can we use diffusion models in stroke and MS? Because diffusion models of learning, particularly those which are diffusion weighted images and diffusion tensor images, are proving to be highly valuable in management of both stroke and multiple sclerosis. Again, they can be used in early detection and diagnosis to detect acute ischemic strokes by identifying abnormalities in water diffusion within the brain tissues and lesion segmentation from MRI scans and predicting outcomes of stroke treatments. It involves forecasting the recovery of brain tissue and the potential for functional recovery. In multiple sclerosis or MS, one can use them for lesion detection and classification, detect and classify MS lesions, both active and inactive lesions in the brain and spinal cord, which is important for the monitoring disease activity and progression. Assessing the white matter in the brain, white matter integrity in the brain. DTI, which is a type of diffusion imaging, is particularly useful in assessing the integrity of white matter tracts in multiple sclerosis patients, understanding the extent of neurodegeneration and its impact on cognitive and motor functions. In MS, monitoring the disease progression, diffusion models can track changes in the brain structure over time. You take the original image, add noise, and see how it progresses, and maybe diffuse back to see where it might have started. And thus it provides insight into the progression of MS. This information is very valuable for adjusting the treatment strategies and improving patient outcomes. One can use diffusion models by uh, evaluating the treatment efficacy by comparing different diffusing image data before and after treatment. Then these models can evaluate the efficacy of therapeutic interventions. I think the final one that I took the example of was transfer learning, because I found that this has transfer learning has tremendous applications in in not only the diagnosis but also the treatment of neurological disorders. And in transfer transfer learning, how does transfer learning work? Uh, Basically, you take a model which is trained on existing large data set of a related task. For example, a neural network might be trained on a massive image data set like ImageNet to recognize general objects. And then this large training set, this large neural network, which is already trained on a, a large data set, then we can do the transfer of this learning to specific tasks. That means smaller adjustments can be made in the network, but it has already learned a task from a bigger model. So thus it can save tremendous amount of time and data. So the pre-trained model is adapted to a new but related task, and this involves fine-tuning the model on a smaller task-specific dataset. For instance, the pre-trained image recognition model could be fine-tuned to identify specific medical conditions in MRI scans. The advantage is that you don't have to retrain the neural network on each task. You already have a very large understanding and trained, and then you're tuning it to specific tasks. It can reduce training time since the model has already learned general features from the pre-training phase. It requires less time and computational resources to adapt to the new task. It gives improved performance because transfer learning often leads to better performance, especially when the new task has limited data. The pre trained model brings in valuable knowledge that helps in achieving this higher accuracy, and it provides efficiency with limited data. It is particularly useful in scenarios where collecting a large amount of labeled data is challenging. And the pre-trained model can effectively leverage the small data sets for new tasks. It's very relevant to neurological disorders because large data sets, either in stroke or in MS, are less available. I have actually tried to collect two data sets that I will give as an example, but it was a challenging task for me to find the data sets for building the actual systems. Uh, so I've given one slide on the application of transfer learning to stroke and MS, motor imagery, and BCI systems. Transfer learning can be used to adapt models trained on healthy individuals to work with stroke patients. So this is very effective because the data on healthy individuals is tremendous, but then we have to train or fine tune the data for persons with neurological persons with neurological disorders. So this involves fine-tuning pre-trained models to recognize and interpret the specific brain signals of stroke patients during motor imagery tasks. For example, a study used a combination of EEG-net and fine-tuning techniques to improve the performance of MI-based BCI systems for stroke rehabilitation. Uh, this particular approach, actually, I have a reference here, but this particular approach significantly reduced training time and improved classification accuracy. You can use the transfer learning to transfer data from session to session. Transfer learning can be employed to enhance the consistency of brain computing interface performance across different sessions for the same patients. So this can help in maintaining the effectiveness of rehabilitation over time. In multiple in MS, cognitive training, transfer learning can be used to adapt cognitive training models developed for other population to specific MS patients, and this can help in involving improving cognitive functions such as memory and attention, which are often impaired in MS. And predictive modeling, transfer learning can enhance predictive models for disease progression in MS by leveraging data from related neurological conditions. Uh, so this can lead to more accurate predictions and personalized treatment plans. So I thought that it might be very relevant to uh, because a lot of the data for strokes and multiple sclerosis can be captured through smart wearables and phones. And for example, smartwatch because or BCI devices, and they can give real-time data for diagnosis as well as for rehabilitation, and adjusting the exercise patterns, because you can see what the blood pressure is, whether or what is the heart rate, what is the temperature through these devices, whether it is phone, whether it is smartwatch, whether it is a BCI device. And there are three data sets, but the most important are the multiple sclerosis core data set, which is the second data set. And this core dataset for multiple sclerosis consists of 44 variables in 8 categories covering demographics, comorbidities, disease history, MRI results, and treatment plan. By the way, this citation 16 I have at the end of the presentation, and once I post the presentation, you'll be able to refer to citation 16 and citation 17. I kept the same citation number because it relates to some of our work, and I thought it might be helpful for the audience to refer to. So I have provided the actual citation, citations 15, 16, 17 at the end of the presentation, and it will be available to the audience. So this data set is highly useful for modeling disease progression and creating personalized rehabilitation plans. Uh, and it allows us to assess both the motor and cognitive impairments caused by MS, and enables the development of AI-based algorithms for predicting relapses and planning long-term rehabilitation. So one data set is on MS and one data set is on stroke prediction. And stroke prediction data set is a little smaller. It provides 11 clinical features for predicting stroke events. The idea is that if anybody in the audience or whoever watches this wants to do their own experiments, and so this provides a ready set of available data sets for the people to work on. So I thought I'll give a very quick generic description of VR AR and how this might be used and what we have working on as a proof of concepts. So virtual reality is immerses users in a fully virtual environment, usually through headset, and isolating them from real world to interact with a simulated space. So it's very immersive. You don't see anything outside. Whereas in augmented reality, it enhances the real world environment by overlaying digital information, often using smart glasses or headset. So here you have the real world as well, whereas in virtual reality, you have the whole environment is fully virtual. So, what are the advantages of AR VR for stroke and MS diagnosis and monitoring? Uh, Enhanced motion capture. So, one of the things you may note that you can capture, for example, the wearable devices, whether it is smartphone, whether it is smartwatch, they will have accelerometer, gyroscope, and various other sensors. Various other motion sensors, as well as sensors to check the temperature and all that. But you cannot visualize whatever is coming, or even if you cannot visualize by integrating all of these sensor inputs together. Whereas in AR VR, the advantage is that you can, through a head mounted AR VR, you can monitor subtle head movements and all the data in a virtual visible environment. I kind of created a diagram, and you can see that here this person has a VR environment, and you have a diagram which shows that what is the heart rate, whether the person is in a good form doing exercise, and then can adjust the exercise accordingly. So it is unlike wearables, AR VR can visualize data directly in front of the users, and I thought this was a very key component of AR VR systems as opposed to just the mobile phone or smartwatch or any BCI device. So it can provide real time insights into body and brain health. and it provides virtual avatars. And you see the example for guided exercises and instant feedback, encouraging proper movement and building patient confidence. So I created one small slide on how AR/VR may be used in stroke and MS, and the idea is motor functional rehabilitation. AR/VR can be used to create immersive environments where stroke patients can practice with motor skills. These are very real-time feedback and can be tailored to patient specific needs, thus enhancing the recovery of upper and lower limb functions. Cognitive rehabilitation, VR can simulate real life scenarios to help stroke patients improve cognitive functions such as memory, attention, and problem solving. It's very much like creating games for various types and then let the user play various games and then not only diagnose but also rehabilitate using these games. So balance and gait training in AR/VR is very effective in balance and gait in stroke patients. These systems provide visual and auditory feedback to help patients correct their movements and improve the walking patterns. And then these are also home-based rehabilitation because you can put the devices you can the individuals can take these devices with them, or they can just buy them and they are available at home while being monitored remotely by healthcare providers. Similar things for MS. You can have upper limb rehabilitation in MS patients through immersive VR environments by making repetitive exercises more engaging, which can lead to better adherence and outcomes, better balance and gait improvement in MS patients because they provide a safe and controlled environment for patients to practice and improve their mobility. And cognitive and mood enhancement. By again creating various games has shown promise in improving cognitive functions and mood in MS patients. While there is more studies are needed in the for example, for stress testing, for the state of individual, whether a similar environment may help improve an individual or will create make it worse, but it requires to be really tested. And then patient engagement and motivation. The interactive nature of VR and AR makes therapy more enjoyable and motivating for patients because the increased engagement can lead to better adherence to rehabilitation programs and improved outcomes. So I kind of talked about it on cognitive therapy, psychiatric assessments, and rehabilitation, and I reproduced the same figures to assert what I have referred to in the previous slides. And I want to give a very brief one slide of what do we need for AR/VR environment, and then I'm going to talk about a small proof of concepts, one or two slides, and then I'll be ready to take the questions. So for AR/VR environment, the development toolkits are Unity. This is what we have mostly used. It's a popular game engine. It is used to create both AR and VR applications and supports a wide range of platforms. Then there's Unreal Engine for high quality graphics. Arkit, it is Apple's framework. Arcore, Google's framework. Vuforia is an SDK for creating AR applications that can recognize and track images. The programming language is C Sharp. It works with Unity, C++, used with Unreal Engine for VR applications, JavaScript, Python, and Swift. And hardware components, again, very high level, head mounted displays, uh, devices like Oculus Rift, HTC Vive, and Microsoft HoloLens, motion controllers that allow users to interact with virtual environments such as Oculus touch controllers and tracking systems. These are technologies that tracks users' movement and positions, such as sensors used by HTC Vive. So most of these sensors have accelerometer and gyroscope, which basically these readings then one can use to interpret and analyze the data of movements, gait, balance, etc. A very proof of concept smart mirror is basically you have a mirror and you have a face recognition system. So And once you recognize that face recognition system, then based on the movements, it can not only do digital diagnostics, uh, but also recommend uh, the exercises for a particular application. And the idea is that some of the methods that we have discussed earlier, for example, transfer learning, diffusion models, recurrent neural networks, the way we have approached it is that we test all these models offline. By offline, what I mean is on regular computers with all the data sets, and then use Unity to implement it on a smart wearer with a Raspberry Pi on the back of the mirror, and that kind of processing the systems has already learned. So the algorithms are already there. So we implement those algorithms in on the back of the system. It has been challenging, but I think we are making very good progress and hope to have a prototype very soon. So I think I want to stop here. Thank you very much. I uh, did take almost a full 1 hour, about 50 minutes. That is what I have promised to Vishnu. So about 52, 53 minutes. So thank you very much. And uh, I believe 52 minutes, Vishnu. So I think somewhere in that range. So I'm open to questions now. Thank you very much. Thank you for listening to.
Yeah, I have a question. Hello.
Yeah,
Yes.
go ahead, Hisham.
Yeah. So my question is, I am looking at bio-inspired
I
AI.
cannot hear you very well. Can
Yeah, I am looking into bio-inspired AI. How we can learn from biological systems to improve our AI. How we learn from how the brain works to improve our AI. So one of the things I sent you an email about it. You can read it. For example, you are looking at how a the neuron talk to each other and synchronize the timing of certain events. So how
Yeah,
we,
I think I did read your email as well.
yeah,
And so the thing that comes to my mind, and I have to think a little bit more deeper,
yeah,
is that BCI devices specifically. So, for example, 52 channel BCI device, or even more channel BCI device, once you put it on, mount it on the head, and those can give you real time activity in the brain. And
yeah,
those activities, when can transfer, I would say, some of the earlier experiments we did, we wanted to transfer it through wirelessly, but it drops all the signals. So you have to have a wired connection of a BCI device. We had a 52 channel device. So you have mounted on the head with 52 channels, and and we gave some simple exercises, for example, addition, subtraction, and so 10 seconds of additional subtraction exercise, then a rest period, and then again give an exercise, and then we see the activity in the brain. And to so we do that and then map it to a neural network, and then see how they can run uh, in a synchronized fashion. That is,
okay. So,
feed the input from the BCI device to, but make it wired, either through a USB connection from the BCI device to the computer. And it doesn't really work very well on simple computers. You have to have a computer with large GPU and slightly more processing power. Uh, and you link it to the device, to the computer. So BCI device connected through a wired connection to the computer. And once you have these spikes and you have a neural network on the computer, and you try to synchronize it. We haven't done that. What we have done is that we take the BCI signals and then train the neural net, for example, either transfer learning and so on, and feed it directly to interpret it. But we have not done exactly what you have referred to in your email of synchronizing these two activities.
exactly. So, but what is the name of that device that you can use it to? to see what is happening in the brain. BCI, I missed the name.
Yeah,
The,
PCI device. I think I can tell you the name. It's forgetting. It's in one of the papers that we had. So this is a 52 channel BCI device, and our university has that. It is not, for example, uh, very simple BCI devices you can buy from Amazon, but they don't work very well. But you have to have a clinical grade BCI device that you can put it on the head, and that will capture the brain activity, the EEG activity in real time.
and sorry, can you spell it? BCI device. What is this? I don't know.
BCI, brain computing interface device.
Brain computing interface device. Got it.
BCI device,
Yeah,
brain computing interface device. So you have 52 channel device, you mount it on the head, and because of the conduction, any activity, EEG activity in the brain, you can transfer it to the computer in real
yeah.
time.
Excellent. Thank you very much.
Yeah, thank you.
That's great. Thank you very much. Excellent.
Yeah.
I didn't know this.
So I don't see any questions on Zoom or on YouTube. There's a comment, excellent presentation, informative. So, so there are no other questions. Maybe I'll ask one last question. I was wondering if there are any ethical considerations in this, like societal impacts, privacy concerns, security concerns. Uh, are there anything to consider?
I think, Vishnu, I agree with you. I think there are a lot of ethical concerns because and privacy concerns because any of this information can have serious consequences, especially for medical conditions. Uh, and so, whenever we have worked, we have always taken IRB approvals and made sure that the data is anonymized and we don't share the data with anybody. Uh, so but again, for the programs, for the real time testing, I think this has a very uh, there are serious ethical as well as privacy concerns.
Okay, thank you. So I just see one comment on the chat, Zoom chat, informative and enjoyable presentation. Thank you. So I think everyone liked it. Thanks a lot, Professor Phoha.
Thank you.
So I want to conclude the session with this small token of appreciation from us. So I'll grab the screen, hopefully you don't mind. Replace current share.
Should I stop sharing my screen?
Yeah, that will help.
Okay.
So this is, I mean, if it was in person, we could have given you a plaque or something. But in the absence of that, we just wanted to present you with the certificate. I
Okay.
emailed you the certificate. Once again, thanks a lot for
Okay.
taking time to talk to our members. Actually, this event is sponsored by several other chapters as well across the country. So, on behalf of everyone, I sincerely thank you once again, and hopefully, we'll stay in touch.
Okay. Thank you. Thank you for inviting me. It was a great privilege to be able to share my thoughts.
Yeah, thanks. Thanks a lot. And thanks everyone for joining. We'll be ending the session now.
Okay. Thank you.
Thanks.
Okay. Thank you. So we'll log out, Vishnu.
Yeah, we can log out now.
Okay.
All right. Thanks.